So when are we going to have a cure for cancer? I mean, how many times have we heard that question? I hear it because I work for a hospital system. I hear it when I'm out with my friends for drinks. It comes up in all types of circles. And it's not like people are going to eventually one day in the medical field have this light bulb that goes off and we have found some miraculous cure. Like, poof, here we are. This is what we've been asking for, right?
Yeah, it's not that easy. I mean, there's so many different kinds of cancer. There's more than 200 different kinds of cancer. And what's been learned really is that cancer is really as individual as the person who has it, right? Like identical twins could be diagnosed with the same exact cancer, and one could respond to cancer and one doesn't respond to cancer, right? So what gives, really? And how close are we to finding a cure for cancer? Hi, everyone. I'm Pete Kenworthy.
And I'm Macy Jepson, and this is Healthy at UH. You know, the good news here is that while cancer, I don't know that we're going to find a cure-all for cancer necessarily, but we have definitely come a long way since chemotherapy, radiation, surgery were really our only options. And what comes to mind for me is immunotherapy. It is really pushed to the forefront of options.
Yeah, and joining us today is Dr. Ted Tecnis, President and Scientific Director at UH Seidman Cancer Center. Dr. Tecnis, thanks for being with us.
Thank you for inviting me.
So we know what our immune system does, right? It helps us fight off infections and other diseases, but we can apparently train it to fight things like certain cancers. So before we get into specific treatments, I want to ask you what immunotherapy is, how does it work, and I want that high-level view, but I also want to hear how the cells are manipulated to recognize and fight cancer cells.
Yeah, immunotherapy really is the latest frontier, if you will, of our fight against cancer. So it really started, amazingly, back in the late 1800s when Dr. Coley, who was actually an orthopedic surgeon, discovered that a patient who had a tumor on his face, when that tumor got infected with a bacteria, his tumor shrunk. And that sort of sparked a light bulb in his head that said, wait a minute, maybe our immune system, which fights bacteria, can also fight cancer. So remarkably, what he did then is he took a bunch of capsule proteins from bacteria and created a toxin. He called it Coley's toxin. And he started injecting it into people's tumors. And lo and behold, a lot of tumors started to respond and get smaller just by this agent. And this was way before chemotherapy was on the scene. And it was a revolution at the time. But as with many things, it didn't stand the test of time. And as chemotherapy was developed in the 40s and 50s, 1940s and 50s and 60s, Coley's toxin kind of went away. And the whole idea of harnessing the immune system to fight cancer took backseat to radiation, chemotherapy, and surgery. So the concept of immunotherapy has been around for a while. So what is the concept? The concept is that our own immune system is incredibly powerful. It can fight viruses, bacteria, whatever foreign substances in our bodies, the immune system can develop a response to it. And not only can it develop a response, but it can create a memory to that response so that when we're re-exposed to that, we respond to whatever bacteria it was that we were exposed to previously, and it doesn't affect us again. That's how vaccines work. That's how, COVID being the perfect example, if you're exposed to proteins that are on the COVID virus, the next time you're exposed, you have a memory and an immunity to it. So, immunotherapy is in essence then allowing the immune system to identify a cancer and fight it off. The problem is tumors are smart. So tumors have learned as an adaptive mechanism how to survive against our immune systems by hiding from the immune system. They essentially create around them a force field that is really a protein that turns off the immune system. So as our immune cells come and are looking for a cancer, tumors appear invisible to them. So they cannot see them. It's almost like, if you go into a room, and if you haven't been in that room before, you don't know what's in the room till the light's turned on. And our immune cells, in essence, were running around our bodies blind trying to find tumors. So being able to harness the immune system's power to fight cancers is really what immunotherapy is all about. And there's multiple ways to harness the immune system. So one way is essentially to block whatever that substance is that the tumors secrete that make them invisible to the cancer. So those are, the checkpoint inhibitors. So Opdivo, Nivolumab, Keytruda, all these drugs that you hear about, they're called checkpoint inhibitors. And what they do is they turn off, these checkpoint ligands, if you will, not to get too technical, but it allows then the immune system to identify tumors. And those were approved really in 2014, so very recently, and they went into clinical trials within the last few years. And we've seen some miraculous responses to those drugs, particularly in melanomas. That's one cancer that's been particularly affected.
And you're talking about the body doing this by itself, or is what you're talking about pulling our cells out of our body, manipulating them, and then putting them back in?
That's another form of immunotherapy. So immunotherapy really comes in many flavors. One is, being able to turn off the hiding agents, like I described, the checkpoint inhibition, and activate the immune system against the cancer. So that is essentially using our own immune system, but turning off the cancer's defense, if you will. The other thing we can do then, which also uses our own immune system as is, without manipulating it, is developing antibodies, which are little flags, if you will, that go to a tumor, and a tumor may express a very specific protein on its surface. Let's say, EGFR is something that's on the surface of squamous cell carcinomas, as an example. HER2, which is what Herceptin. Those HER2 molecules are on the surface of breast cancers. So if you can create antibodies that stick to tumors exclusively, and the problem is many of these antibodies don't stick exclusively to tumors, but when they can, you then can let your own immune system identify that antibody and then attack the tumor. So that's another way that we can use our own immune systems augmented by these medications. And then the third way to augment our own immune system is to develop vaccines against cancer. So the antibodies go and stick like a flag on a tumor and identify it. The other way we can do it is say, okay, breast cancers express HER2. Let's vaccinate the body against HER2 so that whenever a HER2 molecule is seen in the body, our immune system fights it. And those are the vaccine strategies. So if you can identify things that are unique to cancers and are separate from our body's natural proteins, then our immune system as is can attack it. So there's three ways that we can use drugs to make our immune systems more effective. The final way is what you're talking about, which is taking our own cells out of the body, putting them in the lab, and genetically manipulating them so that they identify a protein on a tumor. And that's what CAR T cells do. So, we're fortunate enough here at University Hospitals to have a cell therapy facility where we can generate these CAR T cells here on site. There are commercially available products as well. But what that involves is drawing a person's blood, just like giving blood, and then the blood is filtered. The white blood cells, specifically the T cells, are taken out of a patient's, are filtered out of the patient's blood, taken to a lab, and then they're genetically manipulated to identify a specific part of a tumor that is not expressed anywhere else in the body. And then those cells, after they're genetically modified, are expanded in the lab, and then they're given back to the patient like a blood transfusion. And then those cells circulate around the body and attack the tumor only and don't attack the rest of the body. There can be side effects, obviously, but those are highly effective treatments. Those are called cell therapies, and CAR T is an example. Natural killer cells, which sound cool, Those are another type of cellular therapy where they don't even have to be from the same patient. Some of those, because they lack surface markers, they can be from you and given to me. So those are called off-the-shelf cellular therapies, and we got investigations going in those as well.
This is so fascinating. This is so exciting. So now we need to dig deep and find out what types of cancers are responding to this type of immunotherapy. So what kind of cancers are we talking about, and what kind of treatments are we using for those cancers?
Yeah, that's a great question. So primarily right now, these treatments are being used for blood-related malignancies. So lymphomas, leukemias, multiple myeloma. So the most effective cell therapies most effective treatments against cell therapies are CAR Ts for acute lymphoblastic leukemias, and those affect children as well as adults. And then diffuse large B-cell lymphomas, so some lymphomas. And the reason that's another very effective treatment. And then there's a new one now for multiple myeloma, which is kind of traditionally what you hear about as being a bone cancer. So, but it is from the blood. And those are the ones that right now we have the best cellular therapies for. The reason is blood tumors, they all start from a single cell. And they tend to be clones, meaning they look the same, just like that first abnormal cell. So acute lymphoblastic leukemia, diffuse large B-cell lymphoma, they have on their surface a marker that's called CD19. That's a very specific protein. It's only on those cells, and they all look like the mother cell, if you will. So the parents look like all the children. That's why the blood tumors are most effectively treated by these therapies, because they all express it. Now, solid tumors, they behave a little bit differently. So pancreatic cancer, anything that isn't a blood-related tumor, when you hear about tumors of organs, those solid tumors start out from a single cell, but then those cells branch out and can look very different. So if you take a pancreatic cancer, all the cells are not the same. There's some that have gone down a path of looking a little bit different than others. So it's harder to target those solid organ tumors because they have very different patterns of cancers. And then the other thing is their blood supply and the environment that they're in is very hostile to these immune cells infiltrating them. So there's a lot of investigation going now into solid tumor cellular therapies.
For all of the hope that this gives us, people always want to know about the side effects, though, because in the past, side effects were not, some people just couldn't handle them. What about here?
That's a great question. So I wish I could say that these are side effect free, the cell therapies, but there is significant risk to some of these cell therapies. Some of the early CAR Ts were a mix, believe it or not, of human and mouse DNA. So you can imagine your body would react to having a mouse floating around in you. So that causes some reactions. And also, there's such a rapid kill of the tumor that you get what's called a cytokine release syndrome. So as the tumor melts away, because a lot of these cell therapies, within 30 days, there's no tumor left from having large, bulky disease. But with all that death in the body, all these hormonal elements get released, and you have wide swings of blood pressure, and you can even have neurotoxicities that fortunately tend to be short-lived, and there's ways to control them, but they are not without their side effects. Now, the other types of immunotherapy, these checkpoint inhibitors that we talked about, the side effects of those, are also well known, and they tend to cause a ramping up of our immune system. So in those folks, people can get arthritic changes, autoimmune diseases like their thyroid doesn't work as well, or they develop, other immune-related side effects that are, again, like arthritis, like, your immune system attacking normal parts of your body. But fortunately, again, those are reversible for the most part if you stop the treatment.
We did a podcast about clinical trials, and there was that assumption that it was always a last resort, and we learned otherwise. What about immunotherapy? I mean, is it only after chemo and radiation, or?
No, that's a great question. So, a lot of clinical trials start when people are out of options. And I think CAR T started that way too. It started as a treatment where people have run out of a lot of options, and now CAR T is kind of the last resort. Checkpoint inhibitors, the same. These medications, particularly with the checkpoint inhibitors, now they've moved into earlier stages of treatment and as part of standard treatment for many cancers. So we're now seeing them in many instances given before surgery, or as part of the primary treatment and not after other treatments have failed. So I can tell you, just to put it in perspective, I think over the last 6 years, the proportion of our patients who were receiving some form of immunotherapy has gone up, 30-fold, and it's now almost 25 to 30% of the therapies that we deliver at Seidman Cancer Center.
Let's talk about the standard of care and where immunotherapy fits in to certain types of cancers, before, during, after.
Yeah, so I think immunotherapy started out as a standalone treatment, but really what's happened now is it's become incorporated into the earlier parts of treatment. So, and the way that has occurred really is, like most things, serendipity. As I said, what primes our immune system is identification of unique proteins in the cancer that our immune system can attack. So what was found with some melanoma studies, again, by accident, is a patient was on immunotherapy and was responding to treatment, but then popped a spot in their lung that needed to be radiated and still had other areas, but the spot in the lung was large and was more life-threatening. So they said, okay, we're going to continue the immunotherapy, but we're going to radiate your lung. So to get rid of that big spot in the lung. So what ended up happening is they did the radiation, and lo and behold, then the immunotherapy started working better. And that's because the radiation killed the tumor, released in it by dying the proteins that, activated the immune system, and then the immune system revved up and fought the rest of the tumor. So by killing a tumor while you're on immunotherapy, whether it be with radiation or with chemotherapy, the immune system is better able to identify the antigens of the tumor and then attack it. So now it's been moved up in combination with chemo and radiation to make it more effective.
You talked a lot about fighting blood cancers with immunotherapy, and that's the main use for immunotherapy right now. And before we get into the hope for fighting
CAR T therapy, not immunotherapy. So, so CAR T therapies are very effective against the blood cancers, but immunotherapy as a whole can be both solid and tumor.
Thank you for correcting me on that. Thank you
Yeah.
for that. And we're going to get to this a little bit more on the solid tumors. But before we move on, I do want to just touch on the recent FDA approval concerning CAR T and multiple myeloma, right?
Yes.
What does that mean for multiple myeloma patients to have that?
That is a dramatic development for patients with multiple myeloma. Multiple myeloma is a disease that for many patients is incurable. I had an aunt who passed away from multiple myeloma. I've had very close friends who have it and have never been able to be rendered in remission. It's something that requires constant treatment and constant observation, and can many times not be controlled and lead to a patient's death, unfortunately. So having this new drug called Abecma, which is a CAR T against multiple myeloma's proteins, is really a game changer for patients with multiple myeloma. There is a chance now with this CAR T therapy that there could be a cure for multiple myeloma. And, the trials have started We enrolled the first patient here at University Hospitals in the state of Ohio because of our experience with these types of trials. And knock on wood, he's doing well so far. And this is really, I think, a game changer for patients who were on this chronic chemotherapy regimen waiting, for the, shoe to drop, so to speak. And now having this as an option really has given hope to many, many patients with this disease.
Awesome. That's great to hear. So I'm glad you corrected me a moment ago that immunotherapy in general is used for both, right? It's used for solid tumors, one way of treating, and then CAR T specifically has been used primarily for blood cancers. What about other ways, the future of immunotherapy, I guess, right? And a lot of that may come with the solid tumor cancers that haven't had maybe as much success with these kind of therapies. What is research showing us in terms of how we'll be able to use this going forward?
I think there's no question that a vast majority of the efforts in research is looking at the mechanisms of resistance to immunotherapy and new ways to harness the immune system to fight cancer. So if we look at what is likely to occur in the future, I think with our capabilities of identifying unique proteins, or what are called antigens, in tumors, and then being able either to vaccinate a patient against those antigens or develop a very targeted, CAR T-like or NK-like therapy to antigens or proteins that are only expressed on those tumors is going to be, I think, the holy grail of immunotherapy. The other big area of research is, checkpoint inhibitors, these, this original therapy that's effective against solid tumors varies widely in its efficacy. So in some cancers, solid tumors, it doesn't work at all. The patient's resistant to it. In others, it works, for most, it works about 17 to 20% of the time, where they get a dramatic response and can put the tumor in remission. In melanoma, it works about 50% of the time. But there's still that resistance to this therapy. So a lot of effort is going into figuring out what is different about those patients who don't respond to these immunotherapy treatments. Can we add a second compound once we understand the way that they develop resistance, so that combinations of a couple of agents could then overcome that resistance, and we can get, the 20, 50% responders up to 100%. So that is a major area of focus, and there's been a lot of headway made in that as well.
Does that get into what I said at the beginning about two people can have the same exact cancer, but respond differently because it's literally as individual as the person themselves?
Yeah, so tumors are, genetically very different, and up until the early 2000s, we treated everybody who had a certain type of cancer the same, just based on how they looked under the microscope. And we know that is, it's I don't want to say it's inaccurate, because you are able to lump all lung cancers that are adenocarcinomas, let's say, together. But morphologic appearance is very different from what the genetic makeup of a tumor is. So even though two tumors may be exactly the same under the microscope, they're vastly different, when you look at the genetic variability in the tumors. So that is kind of the whole concept behind precision medicine. If you and I, both had a skin cancer, let's say, because those are very treatable and curable.
Yes.
But if
we're going to put something out into the universe,
right.
yeah.
So if you look at my skin cancer and your skin cancer, and they look the same, and they're both squamous cell carcinomas, you do a sequence of mine and a sequence of yours, they're going to be very different. And being able to identify those differences wasn't even possible until, the mid-2000s. Now we can say, all right, my tumor has, gene X that it's dependent upon, and yours may have gene Y and Z. So how we treat those will be very different, even though they look the same.
You kind of touched on this when you talked about percentages, but what does this mean just overall about our fight against cancer? I mean, are our survival rates going up?
That's a great question, and yes, they are. So when you look, I always use as the benchmark, the National Cancer Act, which was signed in 1971 under the Nixon administration, and that's where we declared war on cancer. And then, our survival rates for cancer back in those days were a certain percentage. And then we didn't really see changes in that survival rate up until the 1990s. Really, even though we had begun investing more significantly in cancer research, all we really had to fight cancers were the surgeon's scalpel, radiation therapy, which was, effective for some tumors, and chemotherapy. But if you look at the difference in survival between 1991 and the year 2016, there was a dramatic increase in survival rates in cancer. So just in that 2-decade period, cancer survival rates went up very significantly. And a big part of that was our improvement in lung cancer survival. So lung cancer was and continues to be a deadly disease, but using all the genetic markers in lung cancer, we're able to tease out lung cancers and identify better treatments. And the difference in just lung cancer alone, survival, coupled with improvements in others as well, but a large part of it was because of lung cancer, cure rates have gone up substantially just in the last 20 years. And I think it's just the tip of the iceberg. Using genetics, using our genetic knowledge to inform our immune system on how to fight these cancers better, I think we're going to continue to see cure rates for cancer rising and rising on an annual basis. Hopefully to the point where it becomes either we cure it or it becomes a disease we live with. The example I always use is HIV. HIV was a universally fatal disease that there was no treatment or cure for, up until, really the identification of one drug, and then a second and a third, and then when they combined all three, now it's a chronic disease that people live with. And my hope is that that same paradigm will work in cancer care.
This is exciting stuff. I love doing podcasts where we leave people with hope. And you do a really good job of explaining it so that people can really get it. You know what I mean? Yeah. It can't be easy to do. Dr. Ted Tecnis, thank you so much for being with us, President and Scientific Director at UH Seidman Cancer Center. Really, really exciting stuff. Thanks.
Thanks for having me.
And we want to remind all of you that you can find and subscribe to this podcast on iTunes, Google Podcasts, Stitcher, and wherever you get your podcasts. Search University Hospitals or Healthy at UH, depending on where you subscribe.
For more health news, advice from medical experts, and Healthy at UH podcasts, go to uhhospitals.org/blog.